Please confirm that you can see the presentation. Hello?
Yes.
Okay, thank you. So we do not have much to discuss today. I shall just make some concluding remarks with a little extra few points added to what we were discussing at the end of the last class. And then I thought I should also take up one or two tutorial questions in tutorial 9, that is. So today we may not have to stay for the full duration of our allocated time of 75 minutes. So let us just return to the wave character of light. What we are talking about now, discussing now, is actually a part of optics. Just a minute, please. I'm sorry. Just a minute. Yes, I hope all of you can hear me clearly, see the presentation as well. So we were able to show mathematically that light is a transverse wave and it is an electromagnetic wave. So in the case of light, there are two waves. One is a wave in the electric field and the other is a wave in the magnetic field. This is the diagram of that, a simple representation of that. That one is you have two waves. You can't have light with just one wave. If you have a static charge and just the electric field, there will be no light in that. For light to happen, you need to have both the fields, both the electric as well as the magnetic field. They are locked to each other, completely in phase, meaning that when you have the zero displacement of the one field, you'll have the zero displacement of the other. And when you have the maximum displacement of the one field, you'll have the maximum displacement of the other. And similarly, when you'll have the minimum displacement of the one field, you'll have the minimum displacement of the other. But they are mutually perpendicular fields in their planes of oscillation. For instance, in this diagram, the electric field is oscillating on the XZ plane, and the magnetic field is oscillating on the YZ plane, Z being the direction of the propagation of the wave. Remember, E crossed with B will give you the direction of the propagation. So E cross B is the direction of propagation. We discussed this point in the last tutorial. I would just like to return to this one particular word, polarization. It's a transverse wave as shown by polarization phenomenon. What do we mean by polarization? By polarization, it is meant that the electric field will be confined to only one plane and the magnetic field will be confined to another plane, and the two planes will be orthogonal to each other, perpendicular to each other. So they will never get mixed. They will be completely separated, electric on one plane, magnetic on the other, and as such, they will be confined, and the two planes will be orthogonal, and the direction of propagation will be perpendicular to both the directions of the electric and the magnetic fields. That is how it is. So that was the point I thought I did not discuss in detail in the last class. So transverse wave, electromagnetic wave, transverse wave, wave in the electromagnetic field, electric and the magnetic field as you derive them from Maxwell's equations. And light, as we understand it to be, is merely a part of a much wider electromagnetic spectrum. The visible light, the kind of electromagnetic radiation under which we see the world around us, ranges from 400 nanometers to 700 nanometers, or equivalently 4,000 angstrom to 7,000 angstrom. So 10 nanometers make an angstrom. So anyway, no, I'm sorry, it's the other way around. I think 10 angstroms make a nanometer. Right. Now we will just go to a few ideas about waves. We have discussed this thing in the last class. We discussed this thing in the last class, that you have the wave equation. We discussed certain features of the wave equation in our last tutorial that was on Wednesday. And the tutorial problem sheet was divided into two components. One was about general nature of waves, and the other was about the nature of electromagnetic waves. So you have, this is a linear differential equation, linear second order. Second order meaning you have this del 2 del x squared, del 2 del t squared. So second order equation, partial differential equation, meaning that there are two dependent variables there, or rather there's more than one dependent variable. Sorry, independent variable. There's more than one independent variable, in this case two, x and t. So second order, partial, and linear. Linear as in that you just have psi occurring in the first power and nothing else, only that. If you have psi occurring in the first power and in no other form, you can call this equation a linear different second order partial differential equation. So if psi1 and psi2 are solutions, then their superposition, the summation of psi1 and psi2 is also a solution. And I also touched upon the question of initial and boundary conditions, that we are talking about a wave. And as such, a wave is not a point-like object. It's distributed in space, spread out in space. And so you say technical term is non-localized. And so it'll have a starting point and an ending point somewhere. So, I mean, if it's an infinite wave train, then you'll say that the two boundaries are at minus infinity and plus infinity, like that, or zero and infinity, whatever. And the time part captures the oscillatory character of the electromagnetic fields. So in this kind of a situation, you can't have a wave unless you have the oscillation. But you don't always have to have an oscillation to have a wave. Be very careful about that. For instance, I talked about a Gaussian wave in your tutorial. A single spike, a single peak traveling, such as a tsunami, let's say. That's also a wave, but it's got a different kind of a profile. It doesn't have an oscillatory character in time. So anyway, so it's just propagating forward like that. We discussed this in the tutorial. So anyway, so we have, let us say, two such waves. We will be just talking about the principle of superposition. The principle of superposition says that if psi1 and psi2 are two solutions, two distinct solutions of the wave equation, then their linear sum is also a solution. This is known as the principle of superposition. Let us see what we mean by that. We were just discussing that in the last class when we ended. You have got a wave function psi1. You have got, which is drawn by this dotted curve. You have got another wave function psi2, which is also drawn, but by a thin continuous curve. Just a minute, I'm sorry, just a minute, please. Sorry, just a minute. Yes. Now psi1 plus psi2 is also a solution. So let us see what we have over here. Psi1 has zero value at this particular point, and this is the value of psi2. So 0 plus psi2 will just give psi, as psi will be equal to psi2. So that's why this thick continuous function, which is psi2, I'm sorry, this thick continuous function, which is psi, the superposition function, passes through this point. At this point, the value of psi is 0 because the positivity of psi1 is cancelled by the negativity of psi2. So, and here at this point, psi2 has got a positive value and psi1 has got a negative value, and the magnitudes are the same. Therefore, the two values cancel each other, and you have psi going to 0. So like that, you can have all sorts of things. And so the psi will also be a solution of the partial differential equation of the second order. And what will be the solution generally be like? The solution of psi will generally be like this: an arbitrary function of x minus vt and an arbitrary function of x plus vt. Now, why two arbitrary functions? Let us discuss that. See, if you are to integrate a second order ordinary differential equation, let us say d2y dx squared is equal to 0. That's a very simple second order ordinary differential equation. You integrate it twice, and you will get the equation of a straight line. d2y dx squared is equal to 0. will give you dy dx is equal to m, which is a constant, and then y is equal to mx plus c, which is c being another constant. So y is equal to mx plus c is the equation of a straight line. So you introduce two arbitrary constants, and then from boundary conditions, you shall have to integrate. I'm sorry, you shall have to put values to those two constants and fix your integral solution. But here we are not dealing with an ordinary differential equation, we are dealing with a partial differential equation. And as such, instead of two arbitrary constants, it will be two arbitrary functions. Now, this requires some detailed discussion of partial differential equations. I don't want to get into that. It's not needed either. I'm just saying that partial differential equations are not as simple as ordinary differential equations. They have to be solved somewhat differently. It's not as simple as that. And so when you integrate to a second order partial differential equation, this is the sort of thing you will get. Now, if v is greater than 0, let's say a positive value of v, then x minus vt will tell you the propagation along positive x. We have discussed this thing in the tutorial. We discussed this thing in the tutorial, the last tutorial. And x plus vt will be propagation along negative x. So suppose this is x-axis, the f1. So why should you have two branches or two modes, as you say? Well, it's a very simple thing. Suppose you have dropped a stone on water surface. The wave will be rippling out in a circular front in all directions, or both directions, x-axis as well as y-axis. And the equation of the circular front will be x squared plus y squared is equal to radius squared, where the radius is actually a function of time, because as time increases, the radius will increase. But if you were to keep your attention confined only to the x-axis, you'll see the wave propagating forward along one direction and propagating backward along the other direction. So that's why, in general, unless you put boundary walls or anything, a wave will try to move through all the space that is available to it, x and y in this case. Or if you, let us say, explode a cracker on the ground, then the shock wave of the air will propagate in all three directions, x, y, z, upwards, but not below the ground, because the ground acts as the boundary. So it will go along positive direction of x, it will go along a positive and negative direction of x, it will go along positive and negative direction of y, but it will go only along the positive direction of z, which is the vertical direction, but it will not go below the ground. So as you can see, the ground acts as the boundary that prevents propagation along the negative z direction. So different boundary conditions will tell you what the front of the wave will be like. So that's there. We know. I mean, those are matters of complicated mathematics. We don't want to get into that. All I want to say is that the wave function generally admits, as the most general sense, a traveling wave will admit a solution like this. It will have a positively propagating mode and a negatively propagating mode, and the general solution will be a superposition of both the states. Okay, so let us now just look at this part a little, x minus vt business, this thing. So we talk about sinusoidal waves or harmonic waves. Let's try to see. We have a wave function. Let's say that it is happening, there's only a positive propagation, just for simplicity. You can have negative propagation also, but just for simplicity of understanding, we have a function whereby the wave is propagating only along the positive x direction. By boundary conditions, we have stopped the propagation in the negative x direction. And here is an example of what you can have when you have a sinusoidal wave. Notice that the argument of the unknown function f is x minus vt. So for a sinusoidal function, it is a sine k. This f will be this a sine k is packaged in the f, and then you have the x minus vt. That is what it is like. So there are three things to take up here. A is known as the amplitude of the wave. This whole thing inside the argument of the sine function is known as the phase of the wave. And you notice that we have x minus vt as the argument. Then we put a k in front. Now you'll say, why suddenly this k has come up? What was the reason? This is the answer. if you are a little astute, you should be able to figure out what is going on. You see, X has got the dimension of length, T has got the dimension of time, and V has got the dimension of length per time. So length per time into time, overall X minus Vt has the dimension of length. So if I did not have the K, and instead I were to have just written sine of X minus Vt, there would be a dimensional problem. What is the dimensional problem? I believe in your school calculus, you would have heard about or studied about the infinite transcendental series such as e raised to x, sine x, cos x, log of 1 plus x. These are transcendental functions and they are captured by an infinite series. E raised to x, for instance, will be 1 plus x squared by factorial 2 plus x cubed by factorial 3, and like that it goes on. And similarly, here we have a sine kind of a situation. Sine theta is theta minus theta cubed by factorial 3 plus theta raised to 5 by factorial 5, etc. And it goes on. Okay. Now, why is this important? Suppose theta were to have a dimension. Suppose, let's say theta has the length dimension. Then there will be a serious inconsistency. What is the inconsistency? If you express sine theta with theta having a length dimension, if you express it as an infinite series, here you will have this anomaly, dimensional incompatibility. Theta will have length dimension, then theta cubed will have volume dimension, theta raised to 5 will have length raised to 5 dimension, which we really don't know what to call, and like that. So there is this issue of dimensional incompatibility if theta were to have a certain physical dimension. But theta should not have a dimension, and that's why theta is an angle variable. And how is angle defined in the radian system of unit? It is theta is like if you have a curved path, theta is defined as curvature length is s and the radial length is r. So s is equal to r times theta. Curvature of an arc, think of the arc of a circle. What is the circumference of the circle like? 2 pi r, right? And so the angle 2 pi will be equal to circumference by the radius. Think of it, the angle 2 pi, the whole angle, full cycle, circumference is the circular length. Circumference is equal to 2 pi r. Circumference by radius. Circumference is the length, circular length, and radius is the radial length, or linear. So length by length is dimensionless. So the angle 2 pi is actually defined in the radian unit as one length by another length. Therefore, it is a dimensionless quantity. So angle is dimensionless, although it has the unit radian, not to lose sight of that fact. It's always very safe if you work with the radian unit. So theta must be dimensionless. But we know here that x minus vt has the dimension of length. Therefore, we can't simply just write sine x minus vt. So we have to multiply this thing by a quantity that has got the inverse dimension of length. And that is the dimension of k. K has got the inverse dimension of length. Okay. So now we multiply k with everything inside the argument, and we'll get psi is equal to a sine kx minus kvt. And then that will be the same as psi is equal to a sine kx minus kvt plus minus 2 pi. So you are here, you go all the way by a full cycle and come back here. Having traveled an angle of 2 pi, you're back to the same position and sine will have the same value. Or you can go in the opposite direction and come back here, that will be minus 2 pi. Sine will have the same value at the same this angular point. So that's the circular axis, as we call it. And this thing will, incidentally, you can also work with cosine. I keep stressing that fact. You can work with cosine, and there is a certain advantage actually with working with cosine. In the tutorial, we were able to see that advantage. What is the advantage? If instead of sine, I were to have taken cosine, then anything that happens inside with a change of sign as n plus minus, sign, that kind of a sign, will not affect anything happening outside, because cos of theta is equal to cos of minus theta. So that is one big advantage of working with the cosine function. And you can work with the cosine function. There's no problem at all. There is no difference really between the sine function and the cosine function. It is only that if I give you an infinite wave train. Just by looking at the wave train, you'll not be able to say whether it's a cosine function or a sine function unless I tell you where am I fixing the origin of coordinates. Suppose I fix the origin of coordinates here, it's a sine function. I fix the origin of coordinates at the maximum, then it will become a cosine function, like that. So it's simply a matter of where you're starting. That is to say, a shift of a phase of pi by 2, 90 degrees. Okay, so now here we have the circular axis. And on the circular axis, we have a full cycle is given by 2 pi. Full cycle of the argument is given by 2 pi. Suppose you are on the length axis, then what stands for a full cycle on the length axis? On the length axis, a full cycle is one wavelength. For an infinite sinusoidal wave, you are at x, or you go to x plus 1 wavelength, is the same thing. Or you go to x minus 1 wavelength, is the same thing. Meaning that you have a full cycle on the circular path, you go by 2 pi, positive 2 pi. That is equivalent of going by 1 lambda on the length axis. Or you go by negative 2 pi, minus 2 pi, that is the equivalent of going by minus 1 lambda along the negative axis. So basically, if you go by 2 pi, you go by 1 wavelength. 2 pi on the circular path is equal to 1 wavelength on the linear axis. Okay, so x can go to x plus minus the wavelength, and your function will still be the same. So this function is equal to this function, a sine kx minus kvt. So instead of x, I have now written x plus minus lambda. So you just have kx plus minus k lambda. So if I compare this with this formula with this formula, so we compare, making this comparison, I should be able to see that plus minus k lambda is equal to plus minus 2 pi. Therefore, k is equal to 2 pi by lambda, and this is known as the wave number. As you can see, we said that k must have the dimension of inverse length. Indeed, it has, because k is equal to 2 pi by lambda. 2 pi is just angle in radian unit, dimensionless. And lambda is wavelength. It has the dimension of length. So 1 by length is the dimension of k. In 3 dimension, incidentally, we are just talking about, although I don't want to labor this point, we are talking about a wave propagating only in one direction. But then a wave can propagate in all 3 directions. Certainly a wave can propagate in 2 directions. Water ripples, you throw a stone on placid water surface, the ripples propagating from the circular wave propagating from the point of impact is traveling in 2 dimensions along the x-axis and along the y-axis. Similarly, if you explode a cracker or a bomb, the air waves will be propagating along the x-axis, y-axis, and the vertical z-axis. So it's for such a wave, k into x will be replaced by vector k dot vector r. And then this thing can be written in your familiar scalar product form, kxx plus kyy plus kzz. So that is what it is. But anyway, let's not worry about the 3D part. 2D, 1D is instructive enough, and it'll give you all the ideas clearly. Now, what we have seen in terms of the phase part, we can also see in terms, we have seen also in terms of the length part. Now we can see the same thing in terms of the time value. Length, so phase angle, length, and time. Let's see how. I said a full cycle in the angle variable is the phase. A 2 pi phase. A full cycle in the length variable is 1 lambda wavelength. 2 pi phase and 1 lambda wavelength are the equivalent of each other, except that the former is in the angle variable and the latter is in the length variable. Now, what about the time variable? A full cycle in the time variable is the time period of a complete cycle of the wave. So what you have for t is the same as having at t plus minus the capital T time period. So what we did over here for the length variable, we can now do it for the time variable. We will substitute the small t with small t plus minus capital T. And so what we will have here, it is that x minus vt minus plus vt. Note that we had plus minus here, but since there is a minus sign before t, you will have to write this as minus plus vt. Okay. So then the next thing will be kx minus vt minus plus kvt. And also the same thing you will see for the sign part. So kx minus vt. So whether you go the forward or backward, it doesn't matter in the phase. So minus plus 2 pi. So when you establish the equivalence between these two, 2 pi is equivalent of kvt. 2 pi is equivalent of kvt, but k is equal to 2 pi by lambda. Just a while ago we showed that. So this 2 pi and this 2 pi will cancel, and your capital T, so 2 pi and 2 pi will cancel, and capital T by V by TV by lambda will be equal to 1. Therefore, T will be equal to lambda by V. And V, therefore, is equal to 1 wavelength by 1 time period. And that is how it should be. 1 full wavelength, how much time is taken to travel 1 full wavelength for the wave is the time period. So that is the velocity. But then T also can be established from another point of view, namely the frequency. And so T is 1 upon the frequency of the cycle. So then V can be written as lambda is into 1 by T, can be substituted by T, substituting 1 by T with nu from this formula, we will get V is equal to nu into lambda. Okay. But then V is equal to 2 pi nu. And I'm sorry. The next thing is that I'm multiplying this equation, V is equal to nu into lambda, multiplying this equation by 2 pi and dividing by 2 pi. And 2 pi nu is the angular frequency omega, and lambda by 2 pi is k. So k is equal to 2 pi lambda, omega is equal to 2 pi nu. Therefore, V can also be written as omega by k, and this is known as the phase velocity. In school, you would have studied V is equal to nu into lambda. Here, this thing, the same thing, can be recast in slightly different form. V is equal to omega by k, that is the phase velocity of the wave. So in the case of light, V is equal to C, electromagnetic wave, that is, V is equal to C. And if V is equal to C, then C being a universal constant, it is the same everywhere in all frames of reference. The speed of light does not change. Anywhere in the universe, it has the same value. So as soon as light is propagating, C will be equal to nu into lambda. So in this equation, V is equal to nu lambda, you have got 3 unknown quantities. So you will have to prescribe 2 values for the third to be known. I prescribe V and nu, I know lambda. Or I prescribe nu and lambda, I know V, and like that. Or I prescribe V and lambda, I know nu. So I have to prescribe 2 things to know the third thing. But if I were working with an electromagnetic wave, as it comes out of Maxwell's equation, propagates with the speed c, in vacuum that is, in vacuum. It propagates with the speed c in vacuum. Therefore, one thing is already known. So to know, so we now have 2 unknowns in such an equation. And so to know those 2 unknowns, only 1 unknown value has to be prescribed and the other will be known. So you prescribe the value of the wavelength of light, you'll know the frequency immediately because c is a constant quantity, like that. So light is a very special kind of a wave. In the last class, we discussed that light, one very important point of light is that light travels more slowly in a medium than in vacuum, which is completely opposed to our understanding of the nature of waves as in acoustic waves. In the case of sound, sound propagates in a medium more readily than in, sound doesn't propagate in vacuum at all. Thicker the medium, more dense the medium, sound has greater ease of traveling. So, but light is nothing like that. Anyway, this is the wave nature of light, and this all is a consequence of Maxwell's equation. We have come to the end of our formal discussion of electromagnetic theory. This is the final package. I call your attention to divergence of E is equal to 0, divergence of B is equal to 0, curl of E is equal to minus del del T of B, and curl of B is equal to mu naught epsilon naught del del T of E. This thing is the huge contribution of Maxwell. All of our communication technology, all this talk of space technology, everything. I mean, you are ICT engineers, right? Information and communication technology engineers. How do you send information? By communication, by communicating. And how do you communicate? At best, you communicate at the speed of light. All of those things would not have been possible if Maxwell had not introduced this. He did not have the great insight of introducing this whole idea of mu naught epsilon naught del del T of E as a time varying electric field, and epsilon naught del del T of E is the displacement current as he gave it the name. So without it, much of modern world would not have been possible, and it also has got very important consequences. I'll just touch upon that. I mean, physics went beyond Maxwell thereafter, thanks to Einstein. And Maxwell was responsible for letting Einstein go along the direction that he eventually took. Suppose I'm ending the course on this one last question. Suppose you were to travel at the speed of light. This is a light wave that is propagating. Follow carefully. This is an important question. This is a light wave that is propagating. So you are also traveling, let us say, at the speed of light alongside it. Then your standard experience will tell you that you will see the light wave to have zero velocity. You will say, how so? Very simple. Take the example of two trains traveling in the same direction along parallel tracks. You might have occasionally experienced such a thing in railway travel, railway journey, that two trains are traveling in parallel tracks in the same direction, and viewed from one train to the other, it would look like there is barely any movement at all. And especially if the two trains are traveling at the same speed, you will see passengers of each train will see the either train to be static. But not so. If you look out of the window in the other direction and see the ground, you'll actually see that you're moving very fast. So with respect to the ground, you're moving. With respect to the other train, you're static. That is the relative velocity of different frames of reference. So shouldn't you experience the same thing with light? Yes, you should. That is a matter of common sense. So if I travel alongside a light wave at the speed of light, then the light should be seen to be static. Light should not be moving at all. But that is a rather serious problem from another point of view. You now follow the way Einstein thought. That is a rather serious problem from another point of view. The velocity of light depends on the electromagnetic character of the medium through which it is traveling. C is the speed of light. Epsilon naught is an electric constant of vacuum. Mu naught is the magnetic constant of vacuum. So when you say light is an electromagnetic wave, this is the mathematical statement, equivalent mathematical statement. Okay, so suppose light is traveling in vacuum. You know, all of space is mostly vacuum, and you are a space traveler. You're traveling in a spaceship that is also traveling at the speed of light, and so both you and light will be static with respect to each other. That's problematic from another point of view. Just because the speed of light has changed from your point of view, from your frame of reference, the speed of light has changed. Which means if something is changing on the left-hand side of this equation, it's a very simple argument, really. If something is changing on the left-hand side of the equation, then the right-hand side of the equation will also have to change. What is going on over here? Just because you're traveling at a certain speed, the electric and the magnetic character of vacuum is changing. That is the intriguing point. Just because you are traveling at a certain speed, if you're standing with, you're a static observer, and light is traveling past you with the speed c, and which means that electric and magnetic constants of vacuum, its permittivity and permeability of vacuum will have these two values. But if you're traveling at the speed of light or at certain other speed, then the speed of light will change. And if it does change, then it means that these two values will also change on the right hand side. Basically, that is to say that the physical character of vacuum is changing just because you are in a state of motion. That is a little difficult to reconcile. And indeed, this is what happened. When Einstein tried to reconcile Maxwell's conclusion, this conclusion derives from Maxwell's equations in free space. This conclusion. And what is Einstein trying to apply on that? Einstein is trying to apply Newtonian mechanics. When a train is traveling, you are traveling with respect to the train at the same speed in another train. Viewed from each train, the other train would have static, will have zero velocity. So that is exactly the way we solve Newton's equations. So Einstein is tried to reconcile Newton's mechanics. As I said, all of physics starts with laws. The fundamentals of electromagnetic theory are the four Maxwell equations. I mean, all that we have done in our course is to understand the nature of the electric field, the nature of the magnetic field, and how the physical features of both the electric and the magnetic fields can be expressed in mathematical language. And these four equations are that mathematical. Well, of course, I mean, there is a little something to the right-hand side in general. The first equation will have rho by epsilon naught, and the fourth equation will have mu naught plus J, that's ampere. And rho by epsilon naught will be Coulomb packaged through Gauss, restated through Gauss. So basically, all that we have done is establish the fundamental laws of electromagnetic theory. I mean, that has been the objective of the course. The fundamental laws of electromagnetic theory from first physical principles and expressing them in the mathematical language as established by Maxwell for the first time. And in so doing, we also realized that light really is a subset of electromagnetic theory. But to return to Einstein once again, what he realized, now this is just like this whole business, mu naught, epsilon naught, del del T of E, is the startling conclusion of Maxwell, which leads to everything that you are going to study in your student life, ICT, information and communication technology. So it is that the one great realization of Einstein is that what you see in your scale of the universe, that is to say that you are traveling in a train at, let us say, 60 kilometers an hour. A train is traveling next to you at the speed of 60 kilometers an hour. Viewed from your train, the other train will have zero velocity. And viewed from the other train, your train will have zero velocity. But now, instead of two trains, you think of one light beam traveling at 3 lakh kilometers per second and another light beam traveling parallel to it in the same direction, that is, with the same speed, 3 lakh kilometers per second. Viewed from one light wave train, this is a wave train, viewed from one light wave train, the speed of the other light wave train will not, NOT, will not be zero. It will still be 3 into 3 lakh kilometers per second. One light wave is traveling at 3 lakh kilometers per second. Another light wave is traveling at 3 lakh kilometers per second. Both these values are measured by an observer that is standing static on the ground. But viewed from one light train, the other light train will continue to have the speed of 3 lakh kilometers per second. That is what Einstein showed. And he realized that Maxwell was more fundamentally correct than Newton You would have to be a brave man to say that Newton was not completely correct. But that is what Einstein said, and that is what that's his greatness. But he realized that when objects move very fast, close to the speed of light, or at the speed of light, then our commonplace understanding of Newtonian mechanics does not hold. You'll have to modify Newtonian mechanics, and that is what Einstein did. His theory of relativity was a modification of Newtonian mechanics, but but in so doing, he left Maxwell intact. That Maxwell is more correct. I mean, this formula is correct. C will not change, and therefore the electric and the magnetic character of vacuum does not have to change when you're traveling at the speed of light next to another light train. Your spaceship is traveling at the speed of light, and another spaceship and a light beam is traveling parallel to it. Viewed from your spaceship, the light beam will continue to have the speed of 3 lakh kilometers per second, and therefore the electric and the magnetic character of vacuum will remain what they are. That is what. But then, just one final point. Einstein did not spare Maxwell from another point of view. I think he would have studied something at school, namely the photoelectric effect. The photoelectric effect says that light is not a wave, but it is a particle. Maxwell's equations lead to the wave character of light. Light is a wave. This was experimentally seen by through Young's interference experiment, diffraction experiment of Fraunhofer and all those people. But so light is a wave. Nobody doubts that. We have discussed this thing so much. But Einstein wouldn't be Einstein if he were to just have stopped short of saying that Newton was not correct. I wouldn't use the word wrong. Newton did not give a complete theory of mechanics when objects move at the speed of light or close to the speed of light. But Maxwell is more correct over there. But then Einstein goes again, this time to challenge Maxwell. Maxwell is not completely correct in as much as the behavior of light is concerned. Light is not always a wave. Light can also be a particle. And I believe you're aware of the name of the particle of light. It is called the photon. So Einstein, in fact, got his Nobel Prize in physics for establishing the photon character of light through his theory of photoelectricity. Photo, as in light, electricity, as in electromagnetism. You can see the role of electricity and magnetism in Einstein's approach, both in mechanics as well as in light, and mechanics as in the theory of relativity, as in light, as in the case of light waves and all the things that we have discussed. Since I touched upon interference, I'll just conclude with that one point, although I've not written the word interference anywhere. Light on light doesn't always give you more light. Light on light can also give you darkness. That is the nature of interference. Suppose you have a light wave train going like this. You superpose this light wave train by another light, and you can do that. The solution is valid. You have got one wave function, you superpose that with another wave function, and you'll still get a new wave function. But what will that new wave function show? The displacement function. Suppose you have got a light wave going like this. On that light wave, you put another light wave which is same in phase. The two waves will reinforce each other and you'll have greater brightness. Very good. But suppose you superpose a wave train that is out of phase by half a wavelength or angle pi. I hope you can tally what I'm saying. A full wavelength is the equivalent of 2 pi. Half a wavelength will be the equivalent of pi. Suppose I have a wave like this, and I take another wave which is pi phase off, out of phase by pi. So it is going in the opposite direction, that the amplitude is going in the opposite direction. When you put two such vector functions on each other, they will cancel each other, and the total displacement amplitude, the resulting displacement will be 0. Therefore, when you superpose two light waves which are off by a phase of pi, they will cancel each other. So light on light can give you complete darkness. That is the classic nature of interference. You say that, you know, two of you separately can do a lot of work with each other, a lot of work by yourselves, but you two are not on very good terms. So when I put the two of you to work together, you interfere with each other and no result, no output, no outcome happens. I mean, there is no output. So you interfere with each other's productivity. So that is the nature of interference. Two light waves can interfere with each other's brightness, and you can have complete darkness. Anyway, so those are the points I thought I should make about the wave character of light. I have discussed enough. So that concludes your examination syllabus. Incidentally, I'd just like to touch upon a few points. Your examination syllabus will be the full syllabus, right? Your examination syllabus will be the full syllabus, but of course it is to be understood that there will be greater stress on the material that is covered after your mid-semester examination. I'm sorry about the delay, but I've corrected the tutorials and everything. There were some errors in the tutorial, so I'm hoping that by today or tomorrow your tutorials will be given, all your lecture recordings will be given to you very soon, and maybe in a few days' time, by this weekend, or maybe I'll also give you the lecture notes, and then some supplementary notes I shall supply you in due course. Regarding your examination, your exams are starting on the 13th, and I think your paper is on the last day, 18th. So you still have some time. Today being the 3rd, you still have more than 2 weeks. My advice to you is that, going by your experience of the first examination, the mid-semester examination, you would realize that it's mostly numerical. Maybe a little bit of formula would have to be written here or there, typed, and also maybe at all, if at all, some word or two may have to be typed. So you are now familiar with the way we conduct our examinations, so I don't want to spend too much time on that. Suffice to say that don't write too many things. It's a distraction. But yeah, I mean, that's it. I mean, that's about the examination, the full syllabus. Objective paper, in the sense that you just have to type in numerical values with units and sign and all those things, numerical values, and maybe occasionally a formula to type if at all it should be called for. So with that, I conclude the lecture. I'll just go to a tutorial. We still have about 28 minutes. I'll just conclude, I'm concluding the lecture. I'll just go to discussing a tutorial. There are a few points I thought I should touch upon. Sorry, just a minute. I've stopped sharing this lecture notes. This is tutorial 9. Meanwhile, from your side, if you have any questions or any issues, you're welcome to email them to me. I'll try to, email would be best, because if you write me an email, then the answer could be circulated with the entire batch for the benefit of everybody. Anyway, I'd just like to touch upon a few points in tutorial 9. It's about images, and image problems are not always very easy to work on. You already have the solution, but I'd just like to touch upon a few things. You see, in question 1, you've got a point charge Q that is situated at, I'll just discuss question 1, 9, and 10. In question 1, a point charge Q is situated at a distance A from the center of a grounded conducting sphere and of radius R. Find the potential outside the sphere. So this question is applying the idea of images or image charges. Okay. The same question is extended in question number 9. Refer to question 1. We assume that the conducting sphere was grounded, but with the addition of a second image charge, the same problems become suited for the case of a sphere at any potential V0 relative to infinity. So what charge should be used and where should it be placed? Find the force of attraction between a point charge Q and a neutral conducting sphere. So that is one thing. And question 10 is asking you the potential of an electric dipole is obtained by going up to the order of d by r in the binomial expansion. Carry out the binomial expansion up to the order d by r cubed. In the lecture, we discussed d by r. And so here in question 10, you're asked to go up to the order d by r cubed. And then you comment on the result obtained. So those were the 3 questions I'd briefly touch upon, and then we can stop. So here are the solutions. So as I said, questions 1 and 9, I added a supplementary discussion, right, to which was not discussed in the class. I just added a supplementary discussion. So refer to the figure in question 1. Right, the potential due to both charges at PR is, let's see now. Here you have, sorry.
Sir, the screen is not visible.
Oh, I'm sorry. I think I have, I don't know why. I thought I presented it, started sharing it. Can you, just a minute, I'm sorry. Can you see now? I think you should be able to see now.
Yes, sir.
I don't know what happened. Uh, yeah, I mean, online lectures are no comfort, really. Truth be told, I should be glad when things go back to normal. Oh, yeah. So refer to question 1. In question 1, you have got two charges. So this is the Q and this is the shell with a potential V is equal to 0. Instead of the shell, you think of an image charge that is placed somewhere within the shell so that the negativity of the image charge will cancel the positivity of the positive charge, and here V will be equal to 0. So if the Q negative charge is Q prime, at any point PR, it will be the potential due to this charge and the potential due to this charge. And so here you have that thing. So that's the potential function. But on the surface of the sphere, when the radial function is capital R, here V will be equal to 0. So when V will be equal to 0 on the sphere, this whole thing will be equal to 0. Q by R2 plus Q prime by R1 will be equal to 0. Therefore, you can write this thing. Now refer to the figure in question 9. In question 9, here, there's this thing. I thought that this point could have been discussed. I mean, this supplementary sheet was not there in your tutorial, so that's why I thought I. Now, you have been told earlier you had this dotted sphere is the real thing, the dotted circle, but you're eliminating that. In place of that, you're putting Q prime because this whole thing is at 0 potential. Now somebody is saying that I have placed a charge at the center of the sphere. That charge is Q double prime. So that will give rise to a potential of V naught on the surface. So now there are three charges. This and this will cancel the potential of each other on the surface of the sphere, but this will contribute a potential of V naught on the surface. So what is the full equation? That is what has been done in the supplementary sheet. The charge Q prime at the center will increase the potential at the surface R equal to capital R to V naught, which is Q double prime by 4 pi epsilon naught R. If that Q prime were not there, then the potential at the surface would have been 0. Q prime would have been 0, and that is. So now you have got three charges, Q, Q prime, and Q double prime. The reality is, follow this point carefully, the reality is that you just have actually two charges. What are the two charges? Q and Q double prime. And you have a spherical surface, nothing else. But instead of the spherical surface, you are substituting the spherical surface with an image charge of Q prime. And the effective potential at any point P will be, because of these three charges, two real charges, Q and Q prime are the two real charges, and the third charge, Q prime, is an image charge. So the potential will be due to these three charges. Now, when you have R equal to capital R, V will be equal to V naught. So now let us see. So V naught, so Q prime is placed at the origin of coordinates. Let me go back to the figure. And any point R, small r that is, will be measured with respect to this. Q prime, Q double prime will have, at any arbitrary point P, Q double prime will be a distance R away. Q prime will be distance R1 and Q will be distance R2, like in the first figure. So that is what you have done. And so there you have, so now what you will do is that you write the small r as capital R. So this Q double prime by 4 pi epsilon naught capital R will be equal to V naught. When your small r is equal to capital R, V is equal to V naught, but we have seen that V naught is equal to Q double prime by 4 pi epsilon naught R. These two things will cancel each other. And again, you have the same situation, Q by R2 plus Q prime by R1. So this condition is the same as in question 1, and the same procedure follows. That is what you have done. This really should highlight the fact that a constant potential by itself actually means nothing. Potential can have any value. You can just jack up the potential by adding a constant value anywhere. So this is a constant value that has been added to the surface of the sphere. But what really matters when you are making electrical measurements is potential difference, because unless you have a potential difference, you will not have a force. This is what comes from the concept of conservative fields. Force is the negative gradient of a potential function. Gradient of a potential function. What do I mean by a gradient of a potential function? That the potential is changing from one point in space to another. If the potential were to have been constant, then the gradient would be zero, and therefore the force would be zero. Force is the negative gradient of a potential function. So gradient to be non-zero must have a changing value of potential from one point in space to another. So what really matters is what the force somebody is feeling. Remember, Newton's laws do not mention any potential. The measurable quantity is still the force, right? You can't measure potential really. All that you can measure is potential difference. And so you can have any arbitrary constant added to the potential function, doesn't matter. So that this problem highlights that fact. Let us just quickly go to the 10th question. The 10th question is asking you, I mean, it's a long mathematical question. I've provided you the solution. We discussed these things in the class of an electric dipole. And in that case, what we did was, I mean, we did this, we just took a binomial expansion up to the first order. Right? If you recall that discussion, we said that d by r is a very small quantity. And when you take d by r to be a very small quantity, then d by r squared can be neglected against d by r. So that is what we did in our usual treatment. But here we are not doing that. Here we are going up to the third order. Right. So this is what we have done. This is all binomial expansion. This is school level algebra that we have done. And we go up to the cubic order, third order. And then after that, there will be just, I'm briefly discussing. I'm not going to discuss the mathematical steps. You have the things already with you. And so basically, once you have that thing, after that, you will realize that the final result is an interesting one. That is what I want to comment upon. I mean, I'm not getting into the details of the algebra. The final result is an interesting one because it does not contain the even orders. The final result contains only the odd orders, d by r raised to 1, d by r raised to 3. The square order is gone. And we anyway did not take the fourth order. If I had taken the fourth order, it would not have mattered. The fifth order would have mattered. Why do you think such a thing has happened? Such a thing has happened because of this business. There is a minus here and there is a plus here. As a result, but both of these two things, the quadratic order have got, the two quadratic orders have got the same sign, SIG and sign, as in plus minus. As a result, when you take the difference of the two, right, you have to take 1 by r plus minus 1 by r minus, 1 by r plus and 1 by r minus. When you take the difference, these two things will have a lot of cancellation between the two of them. And so when you take the difference of the two, all the even orders will cancel. You can see the minuses have cancelled, and then in the quadratic order, alpha squared and beta squared, they will also cancel. So there you will see that. And so finally, you will have, there you can see that in the quadratic order, the square order, you'll have these two things cancelling out the quadratic orders. And basically, you'll just be left with the odd order terms. And so now let us see. D by R terms give the standard dipole expansion, right? D by, if you ignore this thing and this formula of a dipole you have worked with. There are no quadrupoles. So dipole, quadrupole, and then if it's cubic order, 2 raised to di, as in 2. And then 2 raised to 3 is 8. So that's why this 8 as in octo, octo as in 8. So that's why this term is called the octopole term, d by r cube. It adds the next order of correction to the potential V. You can immediately make an educated guess. I asked you to go only up to the cubic order. You can go up to any order you want to. In the binomial expansion, this is an infinite order, right? Um, this here, this thing, you see I've written three dots over here, meaning it can go on forever. If you are taking the quadratic order, you can immediately make an educated guess, they will cancel out. You notice that 1 is the zero order. This thing raised to 0, anything raised to 0 will give you 1. 1 is the zero order. 0, 2, 4, although 0 is not an even number, but stepwise it is a part of the same sequence. And so the zero order has cancelled, the quadratic order cancels all these things. The first order survives, the cubic order survives. Then immediately you can make an educated guess that the fourth order would have also cancelled, but the fifth order would have survived. I mean, there is no name for the fifth order, or at least I can't think of any immediately. So like that. So that is the whole point. So yeah, I mean, so I thought I'd just discuss this thing, even follow the math. The math is not very difficult to follow. I thought I'd just hold a little physical discussion on this thing. Anyway, so it is 9:30 now, although as per schedule, we have 15 minutes. So I have completed the course. If you have anything to ask from your side, you can ask me. Once again, I remind you of a few things. Your syllabus is full. You'll be supplied all the study material soon enough, particularly from your book. Your examination will be objective. I think there will be two components to the examination. I'll just have to check with Mukesh, sir. He has sent the instructions to the exam controller's office. I think like before, it will have two components. Both will be objective type. You'll have to type answers, numerical values, signs as in plus minus, and units. And also there may be one or two formulae to type, like last time there was a very simple formula to type, k into 1 plus r or something like that. That was what you had to type. And maybe you may have to write a word or two. So those are roughly your instructions about the examination. You'll of course be sent an email with more details, full details. And yeah, and you'd be going by your experience of the previous exam, you'd be serving yourself well by studying the tutorial problems. So because most of your numerical work will follow the will follow the tutorial problems, but will not exactly be the same tutorial problems. But if you work out the tutorial problems properly, I don't think you will perform too badly in the examination. So as of now, I'm prioritizing the tutorials. That's why I want to upload the tutorial sheets quickly. And then in due course, as soon as possible, I'll also send you the lecture notes. If from your side, you have any question to ask now or later, if it is later, you can send me emails and I shall answer your queries. And if you have any question to ask now, you may do so. Otherwise, we may conclude our course. If you have any question to ask now, you may do so. Otherwise, the course can be concluded. You do not have anything to ask? Hello? Nobody has anything to ask? Somebody is asking something? Hello?
No, sir. We will just mail it once we read.
Yeah. If you have any questions, you are welcome to send me emails. Mail is best because if it's a relevant question, if I feel that it's a question that could be relevant for all others, then I will forward the answer to the entire batch in case somebody else might be having similar doubts. So in which case we may conclude the session. So you may all please log out now. I will send you the recording soon. Nobody has any question. Please log out then.
Hello, sir.
Yes, hello.
Sir, I wanted to ask, sir, can you please repeat why the d by r cube term was known as octapoles?
Oh, it's just a name. Die as in two, right? So it's a It's a 2-point structure, plus and minus, separated. That's a dipole. Physically, you have a 2-point structure. What is its potential going to be like? The potential is going to be a long function. So 2 raised to 3 gives you 8. 2 raised to 2 gives you quadratic. There is no quarter quadratic kind of term. And then 2 raised to 3 is 8. And the word for 8 is octa, as in octagon. So that's why it is called octopole.
Okay, sir. Okay, sir. Thank you, sir.
Hmm. So you may all please leave now, those who haven't done so. I'll log out and I'll send you the recording in due course.
Hello, sir. Did you make any announcements in the beginning of the
No,
lecture?
nothing. I kept all the announcement to the end so that,
Uh,
yeah.
Actually, sir, that because sir, I was able to join only after 5 minutes. That's
Oh, okay. That's not a problem.
thank you, sir.
Thank you. I'll stop the recording now.